It's a good turnout, actually. Thanks for coming, everyone. I'm Neil. I work at Wargaming Sydney, and I'm going to give a talk that's going to be focused on some of the, well, sadly it's going to turn into a little bit more of a post-mortem than here are some interesting things, but hopefully you'll be able to take away some of the quirks that we've encountered when doing some porting work at Wargaming. So, nice empty slide. Basically, I'm a software engineer at Wargaming Sydney. I've worked on World of Tanks and World of Warships. Two of the main things that I've done there are take World of Tanks from working as a basically single-threaded game running on DX9 to running on DX11 and with multiple threads and everything running as well, basically performing a lot better for most of our players. And World of Warships was taking it from the PC to the PS4. So first thing I'm going to talk about is what is porting. Just in case anyone doesn't know, it is turning to, oh wait, no, that's the wrong one. Yeah, sorry about that. Adapting software from one environment to another. So that would be taking from basically either from one console to another, from another API to another. So in the context here, yeah, first one, DX9 to DX11 for World of Tanks, and taking from PC to PS4 for World of Warships. And I'll stop rolling on and move straight on to the engine plumbing part of the talk, which is the bulk of this talk, which is all about the stuff you kind of have to do in your engine, some of the things that you will hit that are problematic, hardware issues, software issues, etc. So for World of Tanks, when we started on it, it was a game that ran on Windows XP. In fact, about 10% of our player base was running on Windows XP at the time, so this was an important thing to preserve. Using only DX9, not even hidden behind an abstraction layer, it was raw DirectX calls all the way through the scene rendering part of it. It was still using fixed function pipeline, as well as shaders, so it was just this big mix of using stuff that should have been deprecated long ago. It was using the D3DX effect library, which is, it's all right, but it only supported DX9, so not very good. 32-bit support as well, not so bad, other than the fact that you're basically limited to 2 or 3 gigabytes of RAM to use. And the game could also play on potatoes, so that's on integrated GPUs as old as the HD3000, 10-year-old plus discrete GPUs that was top of the line when I was at university, and also low-end dual-core machines like the Core 2 Duos, which don't even have hyper-threading, so they are not the greatest CPUs, but you still have to actually, if your players are still running on that, you may as well support it. So what was the process that we'd done? First off, there wasn't an abstraction layer, so we opted to just wrap the DX9 API calls, just one-to-one mapping as a first pass step. That just made it a bit easier to just isolate everything first. We replaced all of the fixed function pipeline usage with basically the shader replacements. Then we just started to work on designing the abstract render interface to basically replace the wrapping that we'd done. We replaced the D3DX effects library with a custom solution known as WGFX, which was syntactically similar. It was set up so that we could later on go and run render work concurrently across multiple threads without the effect library causing any problems. It stripped out some of the features that weren't high performance, such as pre-shaders and stuff, where it's basically just a small jiggles all of your uniforms a bit to save GPU work, and set it up for working with other APIs, DX11. Once that's all working and we're not completely broken, everything's wrapped up, we started implementing the DirectX 11 backend underneath that. Then a long trip of optimization and bug fixing. The other project that I've worked on was World of Warships, which is a similar game engine to World of Tanks. It's actually a version of the Big World client, but they forked at an earlier point. They took our abstract render interface so that they could get DX11 support, but they heavily modified it themselves. They got rid of the DX9 support, so by the time we came to work on it, it wasn't so bad. It was already pretty recent and using modern techniques. And they'd already started the Xbox One port. It was a PC engine. They've got it running on a little bit easier on the PS4 side of things. So the process on this one was a little bit different. Most of the work early on was getting all of the third-party libraries to compile on the PS4. So libraries that had only been built with Visual Studio, getting them building with Clang. Then we have to get the client building, which was a lot of stubbing out things in the engine, going through it and putting what to do, tracking it in Jira so we don't forget about it. We started stubbing out the so that's just initialize the screen, get it clearing or something, start filling out all the bits and pieces, and have a lot of PS4 to do log messages put in. Then on the World of Tanks engine, we had a set of unit tests for the render backend. This was one thing that World of Warships hadn't pulled across from our stuff, so we decided we're going to pull these across. We're going to need them to verify the backends. Once that was done, add PS4 shader support to WGFX. So WGFX basically took some shader input that was just HLSL, rejiggled it, and exported it for various permutations, so with lighting, without lighting, different material parameters. Exported HLSL. For the PS4, it has to export PSSL for that compiler, so had to add support for that. Then focus on basic scene rendering. A couple of months of getting libraries compiling, getting the basics shelled out. We have the scene sort of rendering. It's not looking too great, but it does work. And a little bit later on, we focus on getting first playable. So that's getting all of the networking and gameplay logic working in it instead of just the basic scriptless scene rendering. Still got a few bugs, but nothing too bad. Then another couple of months. we got a lot of work to do. I'd actually forgotten to bring that one up. First playable didn't have to be fast, but after a while, the game's fully playable, running at a solid 30 frames a second. So we were quite happy with that. So what was some of the difficulties that we had to deal with? Well, on tanks, we started off without the unit tests. We actually implemented those later on. So tanks would have went smoother if we had them. But to give you an idea, the unit tests we had, we were using Catch2 as our library. Just create a ton of tests, various stuff like texture format support, resource creation, resource upload and readback, clears, draws, copies, viewports, scissor, resource hazards. Every aspect of the graphics APIs we had to try and test. We actually found bugs in some of the drivers as well, which we had to report because of these unit tests. But it was good to know that, yeah, it's bugs all the way down. Most of the interface was tested, and a lot of it worked by just having reference images. So do a bit of rendering work, compare against a reference image. So simple one, a textured triangle. Pretty self-explanatory. It's textured. Your typical RGB triangle. Frame buffer scissor reference image is just drawing a few things with scissoring in different viewports, and an exhaustive sampler test, which makes no sense when you look at it, but that's every combination of sampler states in one image that we could test against. So when doing porting work, we knew damn well that it would work. It wasn't like we just missed a bit when we were implementing the back end. Another thing that was really useful while porting as well, which I'll mention here, is the replay tests. In World of Tanks, we had generated replays which were just, worst case scenario of circular tanks driving around, shooting at each other, and this is really good at just like testing our worst case performance. On top of that, we had spin tests which move the camera around, measure the performance of various aspects of the levels, and on top of that too, we had actual real game replays which we used for just checking the actual real world performance. But in the case of these tests, the useful part about them was over time, you can see the history of your performance. Like this one, performance is mostly okay up until a certain point. You can see that the frame time's kind of crap there. So you know that there's a change around that point that you can go and look at. Or you can see there's a bit of instability and narrow in and save you having to just run everything through a profile. You can sync back to a change list, have a look at it and go, okay, someone made a change here. It saves quite a bit of time when trying to figure out where the performance has gone bad. But let's go to the actual meat of the talk, I guess. So On World of Tanks, going from DX9 to DX11, we still had to support Windows XP. We had to actually leak some details out of the abstraction. Like, don't ever be afraid to leak details out of abstractions. It's inevitable, really. But one of the main things that was problematic for us was the way that Windows XP handles video memory versus Windows Vista onwards. So on Windows XP, you've got your 4 gig address space and you've got about 2 gig for game. You can, I think, use 3 gig as well, which I believe we've done later. And you've got the other 2 gig there for system usage. So to upload a texture to the GPU, you'd create a staging texture and upload it to the GPU via the API. Then once it's uploaded, staging texture can go away and you've got the address space back. So problem here, when you alt tab out of the game or it loses a device, the uploaded textures are gone from GPU memory. So you've got to re-upload them. That takes time. The solution provided for this by DX9 to make it easier, which is manage textures. So they'll come back once you go back after a lost device, but you forever lose that portion of your address space. That's not very good, and World of Tanks done a lot of work to make sure that their engine was structured well enough to be able to handle all of this, put what's needed in as managed textures, everything else is default on GPU, re-upload when you get the device back. The reason we leaked it out of the abstraction was the higher level code was already handling this and we didn't want to break compatibility at all. So we went, okay, we'll leak it out, we'll use the code that's already there, let that deal with all the problems. Thankfully on Windows Vista, it gets a bit easier. WDDM, the Windows Device Display, Windows Device Display something, sorry about that. But basically the OS handles it for you. You upload your textures via staging, it goes into host memory outside of your address space, and then it just gets paged in as required. You don't have to worry too much about it there, and you have all of your address space. So another thing that we had to leak out of the abstraction was hardware clip planes. Not very exciting, but we actually use these for reflection, particularly on lower end machines. So we decided, because of the differences between DX9 and DX11, which is on DX9 it's a render state call, DX11 it's in the vertex shader you do it. That created a bit of a divergence on how we'd want to expose it. So we just went, screw it, we'll just implement it ourselves in a pixel shader. It's not going to be too much of a problem on performance. So we implement that, just doing a discard in the pixel shader. Fantastic. Performance impact was minimal. We could accept this very tiny hit on the frame rate until we started doing some more thorough testing. Integrated GPUs started being a problem, I think, if I remember rightly. Like, this was a serious impact, like 10, 15 milliseconds or so on the reflection pass kind of performance problem. So we just protocols now have a state added to them for the clip plane, and then we if-def'd in our shaders for DX11 so that if we're building shaders for DX11, we just set it all up there. It's a bit of a divergence. If you try to use the clip plane at the API level, assert and say, this isn't supported, please use the vertex shader one. And on DX11, well, the shader wouldn't compile if you tried to build it for DX9 with that. So also, on World of Warships, when we were porting that one of the obscure things we hit was, at some point during development, we got a bug that said, the metrics don't really add up here. Why is the PS4 rendering more pixels? Yeah, we have a look at this. This is one of the tools that they run auto tests on. So you can see the Xbox One's rendering is at 12 million or something. Anyways, a lot of pixels. The PS4 mainline branch was rendering a lot more. And our PS4 optimization branch was rendering even more. The thing is, we knew we didn't do anything that should have made us draw more things. So what's going on? We have a look at the number of triangles being drawn, and they all line up as well. Right. As it turned out, PS4, the obvious one, PS4's running at a higher resolution at the moment because we're still working on optimization and the best resolution that each console could work on. Yeah, that didn't explain it. It was running at a higher resolution and running with 4 times multi-sample anti-aliasing as well, so it should be rendering a lot more. That only explained the divergence between Xbox One and the PS4 mainline there, whereas our branch was rendering more, and yeah, that's not good. So what actually happened? So anyone who's done work on GPU stuff before probably knows that there's texture compression, like render target and depth compression. We didn't have that enabled. For the mainline branch for PS4 here, we didn't have that enabled. That was to do later on kind of thing that we stubbed out. On our branch, we'd implemented it, which gives us our performance back. But as it turns out, small difference between the Xbox One and the PS4 here was the Xbox One, when you try to measure how many pixels are drawn with the occlusion query, completely just ignored the decompression steps. On the PS4, it actually counted those pixels every time it was doing a full screen decompress. It was counting those pixels. So what do? Just calculate how many and just subtract them. Now the metrics look the same. That's it, running at the same, both consoles at the same resolution. We just went for just winding the metrics back a little bit because smaller numbers look better. And we didn't really care about the details of the decompression steps then specifically because we can measure those separately. So what's next? Yes. Well, the tanks as well, supporting older GPUs, and many of those GPUs don't have up-to-date drivers. So doing what was called the super test, you'd occasionally get some bugs back. It's not working on this GPU. First instinct, update your drivers. No. We had to do a lot of work to support old drivers still. Laptops without OEM updates, so still out-of-date drivers. And then also occasionally there's missing features on older GPUs. For example, in our terrain rendering on World of Tanks was sampling a texture from the vertex shader to offset the position and do the displacement. Some of the older GPUs said, we actually do support this feature, but when you try to query and go, do you support this format? Every format you try just goes, no. It's irritating. Other ones, do you support this? Yes. Can you give me like a filtered position back? No. I'm not going to give you a filtered position, so you have to implement some of those workarounds in the engine as well. Just make sure that if you're supporting older hardware, you've got some fallbacks. Example, because of the age of some of the hardware we supported, and DX9 as well, there was a DX10 feature which we needed for the deferred renderer, which was using like sampling from the depth texture. That's exposed through, it was called int-z, and not all GPUs supported that. Basically, any DX10 level GPU did support it, but if we were running on an older GPU that didn't, we still had to use the forward renderer, so we had to gracefully fall back there. In the resources, I've actually got a link that you might like, which is the ARIS D3D9 hacks, which is a comprehensive guide to all of the hacks that DX9 has you can use and what GPUs support them. Anyways, so some takeaways for this section. I'd recommend do automated testing, and if you start it sooner, it's going to make your life quite a bit easier. If you need to leak anything out of any API, like any abstraction layers, do it. Don't try and generalize everything. It will end up hurting you in the long run, just if you need to get anything platform specific or API specific. Leak it. You can always abstract it later if you want. Measure performance across a wider range of hardware. Like the clip plane example, we didn't test on the integrated GPU that was a problem. We only tested on our top-end AMD and NVIDIA GPUs. So when you're actually measuring some stuff, make sure you're actually measuring what you want. And if you're supporting a wide range of hardware, you're going to be implementing workarounds and fallbacks. Just be happy with that. You're going to deal with it. Hey, this is still sort of engine plumbing stuff, but I felt that threading deserved its own talk. So I mentioned it on World of Tanks. When we'd done some render work, we started getting work running across multiple threads. There were various unexpected things that we hit here. So first, there's a tool that I'm going to let you all know about. If you don't know about it and you're going to do any threading stuff, you will love it. Concurrency Visualizer. It's a plugin for Visual Studio, and you can just attach to your process or launch your game attached to it and record what threads are active in it. So you end up with a timeline view like this, and see in the green there, that's basically where threads are running. Yellow is where things are preempted. Red is where things are blocked waiting on things or just not being scheduled. So you can add markers to this programmatically. We couldn't because we're using the Windows XP toolkit. So we had to do a lot of manual work here and start poking through the captures. But when you know your way around your own engine, you can sort of go, okay, there are all the different threads that are active, find where each frame ends, see what sections of work are. Like this is the scene rendering stuff that's building up command lists. That's our render submit thread that's pushing it to the API. It's the driver thread, and that's it moving over to execute on the GPU. So you can sort of see the flow of data with this. And this is a tool that we use quite a bit on World of Tanks. So first things, one of the things that we'd done was trying to optimize the renderer by putting work into command lists. If you look at this here, you've got the main thread running, and there's API calls being scattered throughout, pushing work to the GPU. It's not keeping the GPU particularly saturated. So when we started batching up work and then delayed the work later on, we managed to get the GPU a bit more saturated. Problem is it's still not actually running most of the frame. So, okay, let's try and make it a bit faster as well by moving the submit thread onto another thread. Nope, still not there yet. So you want to split, you do want to batch up work, but you kind of want to split it up a little bit and get it earlier in the frame if you can, so that you can reduce your frame time and keep the GPU a bit more saturated. So one of the issues that we did hit on, so we added threads and for the graphics work, and we still had to support dual core machines. We had a problem. At one point, there was also some new audio work come in, a lot better sound system added, and it was using a lot more of the CPU. Dual core, we can only be executing two threads at a time. So the audio work was coming in, it's high priority work, and it would preempt anything in its path. And what was happening was driver submit thread was getting preempted, which meant that work was not getting fed to the API. From there, the driver thread was getting preempted, which meant that work was not being fed to the GPU. And the main thread ended up just sitting waiting for a really long time. In this particular case, it was actually occlusion queries. Throw work at the GPU, okay, now wait for the query results after we've done a bit more work, but the GPU was getting completely starved out. There were a couple of issues with this. One of them was the audio thread was actually just using too much, so for the low-end systems, we just had to adjust the audio quality, which was just reduce the maximum number of voices to a bit more sensible amount so that we can actually get the work through. There was also an issue with switch thread and yield processor with the two API calls. Switch the thread was basically you go, can you tell the OS, oh, I'm ready to give up some of my time now. Problem is that can have several milliseconds before you actually get the scheduled again, which means that you can end up you end up yielding for a lot longer than you want, which was not ideal. There's quite a few caveats with which one to use. I would probably recommend reading the documentation on those ones. When we were doing PS4 stuff, we were working, well, PS4 and Xbox. One of the problems that we had was context switching. We had the main thread being switched from one core to another. So the CPU that the PS4 and the Xbox use has the cores split into two clusters, and each of those clusters has a shared L2 cache. So if you want to have work running, and it's working on one core, when it starts reading from memory through the caches, it's going to be reading from its own cache. which is good. Yes? So you get preempted and it gets switched, end up getting rescheduled on another core. If it's within the same cluster, that's fine. It's fine. If the data is still in L2 cache, it will pull it from that one, and that's quick. If you get rescheduled on the other cluster, it has to go the long way. You don't want to be having cross-cluster cache access here. So what we actually done to fix this one, I mean, it's pretty basic. Ideally, you'd have like a job system that's fully aware of all this, but because of time constraints, we just went, stick the game on one cluster, game thread on one cluster, so that it's only ever rescheduled there. Render submit went on the other cluster, so that it's separate as well. Worker threads were just spread across both. They weren't really much of a bottleneck, if I remember rightly, so they were just spread everywhere. Didn't really matter too much. So, also got fighting over cores again. I will not say which console this one was, but one of the consoles, we noticed a problem with the audio thread preempting stuff. Now, we actually tried to, I can see Slater at the back laughing, I think he remembers this one. So, what we done was just sort of a try and see optimization, because we thought, oh, we'll just lock the main thread to one core and one of the clusters. Then it's going to be, all memory access is going to be through the same caches. It'll be great, because we are very main thread bound here. Cool. This is what we kind of expect to see going on. Main thread, running along, fantastic. It's got the pick of all of the time on that core. One of the consoles decided, even though we've got plenty of cores free and not running, we're going to preempt that fucking core. We ended up undoing that change and just locking it to the cluster so that it would reschedule the work appropriately. It's just a bit annoying, just a small difference that you might not expect is the scheduler might do something you don't want. And back to glorious integrated GPUs. So, back to the World of Tanks bit. You've got the main thread running, we've got some API work, then we've got GPU work. It's not very well saturated. When we added the render submit thread, the work pipelined a lot better. So, GPU solid. This is a very exaggerated best case here. So, first case, one core's 100%, and the GPU is at about 50%. Now we've got two cores at 100% and GPU at 100%. Can anyone guess why this turned out to be a problem? Sorry? The US. Not quite. So, integrated GPUs. The GPU and the CPU are on the same die. They're going to be running quite hot. This would be a problem on mobile phones as well. If you're doing a lot of work and doing it as fast as you can, you're going to overheat. If you overheat, you're now at the whim of the heuristics that decide what to throttle. Like, which, does it throttle down the GPU? Does it throttle down the CPU? Which cores does it throttle down? So your performance can start getting kind of janky. Or, I think in one case on a laptop, we ended up just crashing the laptop. Like, it just locked up and rebooted, and that's not very good. This was on a loading screen. On a loading screen where it's got nothing to do, and for some reason running at 300 frames a second is a terrible idea on a loading screen. So we had to just put a frame limiter in here, just make sure that it's actually giving a bit of time for the integrated GPUs to breathe. Also, if anyone's complaining that their game is not running at 300 frames a second on a loading screen, you can probably ignore them. You don't need to be running that fast, it's a waste. Anyways, some takeaways. You've got to tune your workload sizes, and you want to push work early to avoid waiting around. Be aware of contention across cores. Sometimes you might see it when you don't expect it. Take advantage of how your cores and your cache are structured. In general, it's good advice to always know your hardware. I'll just say that again. Know your hardware. It will really help you. Don't make assumptions about what the scheduler is going to do. It could do anything you want. It will generally do something decent, but go measure it and see. And keep your GPU and CPU temperatures in mind, especially on mobile. Even on, I believe, gamers' consoles, if someone's got their console stuck in some locked-off cabinet with no airflow, it's going to get hot. If your game's using it nicely and gives it a bit of time to breathe occasionally, it might might be much longer lasting for them. One of the last things I will talk about is windowing. So this only comes about because we had to make some significant changes to the way this worked in World of Tanks. So when we went from DX9 to DX11, and we're still supporting it, they both interact with the client window differently, particularly with exclusive full screen. DX11 uses DXGI, and that itself sends some additional Windows messages that you've got to handle. I think we had to present on the render thread, and that was sending messages, which was supposed to be handled on the main thread, and it got messy. We had to restructure quite a few things to work around a lot of this. Entering and exiting full screen mode is handled differently on both of these APIs, and we had to also preserve behavior. That was the big one that was the problem for us, which is preserving behavior, because all of the players of the game already expected to be doing certain things. Like if they alt tab out, they expect to be able to come back in, and they know that it's going to take a certain amount of time, and it's not going to do anything weird. Any other third-party applications that they use that might draw overlays, they expect to work. So we just opted for trying to preserve behavior. We also added borderless full screen as well, just to make our lives harder. It only supported exclusive full screen at first. Of course, I knew it was going to break. Anyways, so this is just a table showing the sort of pros and cons of each mode. Windowed is pretty easy to support. Borderless is basically just windowed without borders. And exclusive full screen, yeah, it's a pain in the ass. So what's a pain in the ass about exclusive full screen? Turned out it wasn't as simple as we'd have hoped. I think I spent a good chunk of the time going, why is this so difficult? Surely this is not a problem. Surely we're doing something wrong. No, it's just kind of a pain. Exclusive full screen, in our case we needed to support it because anything before Windows 10, that's exclusive display access, so you have a much lower latency when you're presenting to the screen. On Windows 10, that's not an issue if you've got a window that covers the full screen. That actually gets handled, and it goes, okay, you are rendering full screen, so I will just skip the compositor in this case until it actually needs to do something like overlaying. So lower end machines, yeah, we needed to support it. Then we went around going, surely we're doing something wrong. We tested a bunch of other games out and doing things like alt-tabbing in and out of them from exclusive full screen while they're on a loading screen, locking the machine as they transition from window to full screen, and quite a few of the games done stuff like when you unlock your machine and come back, it'd pop into exclusive full screen and then immediately go back to minimized, and every time you try to go back in, it would just be constantly minimizing itself, and you had to terminate it. There were a lot of weird things that didn't get handled. The players of World of Tanks are already accustomed to some of the quirky behavior that we've done here, so we didn't want to change anything. There's mods, there's third-party applications that inject themselves in, render themselves over the top, so again, we don't want to change this. Some applications will mess with it. Skype for Business will bring up a notification over your exclusive full screen application and tear you out of full screen. Debugging is also really annoying, so when you're trying to figure out what's going on when you're popping in and out of exclusive full screen mode, set a breakpoint, run the game, goes full screen, hit a breakpoint, well, it can't minimize, it's now stuck. It's now stuck there in exclusive full screen in the debugger behind your application. Also, when you're actually changing focus to your debugger, it's going to start changing around messages to say, oh, that application's now not in focus. Let's send a message to tell it that. Now you've just changed everything by observing it. So probably want to use remote debugging for this kind of stuff. But as mentioned before, it was still important to support this mode because I think it was, yeah, this was like a 10% improvement on some setups, having it versus just using windowed modes. So testing it was a pain in the ass. So we've got three different modes that we support here. We've got some test cases. We've got some more test cases. Then we've got the APIs. And then we've got the operating system versions, which have very slightly different behavior. So this was a total ass to test. And to give you an example of just a small number of the test cases that we had to implement. Right, there we go. all of the various things, changing video settings, unplugging monitors, changing desktop resolution, other applications that will show notifications over the top. It's quite time consuming. Basically, you have to just define the behavior up front for it and go, right, this is how we want to handle it. Here are some test cases to make sure that it's handled like that, and thoroughly test afterwards. So from that, the windowing takeaways, it's a surprisingly error-prone area. Avoid exclusive full screen if you can. If you're only targeting Windows 10 onwards, just focus on borderless full screen. It's just a bit easier. In fact, I believe that both Unreal and Unity already do this for you. I don't think Unity's done exclusive full screen for quite some time, if I remember rightly. Might have to check on that. Test your game with messaging software and also with capturing software like OBS. And if you are debugging it, use remote debugging, because that will save you from injecting any messages into your application that you don't want. So a quick recap of everything. Yeah, what it says there. Automated testing is great. Don't go over the top with abstracting stuff. Just leak it if you need to. Measure performance across all the hardware you want to support, maybe even more. Make sure you're measuring what you expect. Threading, yeah, make sure you know your hardware. Tune your workload sizes. Windowing, it's a pain in the ass. So, yeah. Special thanks to these fine people. And if you've got your cameras ready, there's a few resources I'll give you. So, Concurrency Visualizer there. Oh, that was supposed to be white. I'm sure I fixed that. Concurrency Visualizer is great. Use it if you're doing multi-threaded stuff. If you want to know more about the AMD Jaguar, there is Insomniac Games Cache Sim talk, and Naughty Dog's Dog Determination goes into some more details about it. Catch 2 is the unit test library that we used for the ARA unit tests. And if you want to learn a bit more about an antiquated API that you probably won't go near ever again, there's the D3D9 GPU hacks page by Aris. So, thanks very much for coming. And any questions?
What do you use for self-testing?
For self-testing?
Yeah, to get the game to run itself.
Oh, that's all just customized stuff. So we've got a replay system built into World of Tanks and World of Warships as well. And you can, with World of Tanks, you can we have a bots build which will generate replays. So just play the replay, stats come out of it, and that can either be ran through TeamCity or Jenkins.
Okay.
Is that's the answer you're after?
Yeah, I built
Cool.
something similar. I want to see if I can throw it.
Oh, okay, cool. Yep.
For unit tests for rendering, you mentioned having like reference images.
Yes.
Were you able to get away with doing were you able to require a perfect comparison, or was there some need for slush? Because admittedly, really old parts of OpenGL I've used have given different visuals for AMD
Yep.
and NVMe cards, but I don't know if that's still the case.
Oh, sorry. And so, okay, so you're asking if there's any sort of room for things being slightly different.
Yeah.
Depends. Some tests we do have a threshold. Most of them we try to not have a threshold. We want a pixel perfect test if we can get away with it. But there are certainly some differences. One of them was with alpha to coverage produced slightly different results across the vendors. So within our unit tests, we can decide at the point of testing, do we want a threshold value of 1 or 2 kind of thing? Or we can also just have reference images per vendor, which is what we've done for things like alpha to coverage. And we did also have per API tests, like support for that, where there are differences that we have no control over, but they're very minimal. In fact, I can't even recall what tests were different per API.
What did you find actually useful for testing when you were doing the port-in? The metrics afterwards. So you had pixels rendered, you had time per frame, useful metrics?
So that's what useful metrics we had for testing. I can't even remember all the metrics. Will the tanks and will the warships had different sets of metrics they done, but frame time, pixels drawn, how long the shadowing pass took, there's how much memory usage there is, a lot of metrics on memory usage on various systems. If you contact me afterwards, I could probably get you a more comprehensive list if you're interested. I can't recall all of them. There are a lot of metrics that we are measuring. So, yes, that's it. Thank you.